coming to class today, and welcome back to week 9 after a very short holiday, I suppose. Only 1 week of midterm break, but you got your 2 weeks in a row for your midterm assessment. Maybe that is not considered as break. So welcome back to week 9. Yeah. So let me see how many people are already in class. 27 people. I'm so sorry. I still cannot remember how many people who are supposed to be in my class. But starting this week, so I thought of making it a compulsory for everyone to turn on your camera all the way for straight 2 hours. Yeah, because I could see you in class on my second screen. Okay, can you do that now? Sedapnya Syafiqah makan. Makan jugalah. Bismillahirrahmanirrahim. Kalau dalam kelas face to face, tak adalah saya nak makan macam ni depan-depan kamu kan. But you can at least chew anything at your own seats in face to face class. I don't put a rule that you cannot eat in my class. But it's kind of weird for the lecturer to eat while teaching, yeah? So it's very rude, yeah? But since I'm waiting for all of you to turn on your camera, so I'm going to eat my breakfast. So this is my breakfast. Okay, very good that when I ask everyone to turn on your camera, so you make things proper for yourself, how you look, how you prepare your surroundings, prepare your table, and you could also see your own classmates. Yeah, so the feel of having in a face-to-face class is still there, even though it's not so real, but at least we try hard to make sure that we are in a class with other classmates. Yeah, same goes to me. I'm in the class with all of you, so I could see you on my right screen, everyone on your own seats. Yeah, I'm going to change my screen mode to large gallery. I'm not so sure whether if I change to large gallery, you could also change your own classroom at your own screens. I'm not so sure. What do you see now? You could see large gallery kan? Bukan classroom yang dekat kerusi kan? Tak kan? Can you change your own?
Yes.
Oh, when you change, what happens? Everyone semua nampak benda yang sama ke? Tak. Kamu tukar kamu punya surrounding, kamu seorang je nampak
Orang lain pun nampak kalau background. Background ke galeri tu?
Okay, cuba. Siapa yang jawab ni? Afsar cuba. Cuba yang tukar, nak tengok apa jadi kat screen I.
Saya tukar.
Bukan background you, gallery.
Saya dah tukar together mode.
Together mode. You tukar
Saya dah tukar.
Oh. Maksudnya seorang je lah nampak.
Betul.
Tak tahu saya dalam kelas lagi satu, tiba-tiba, okay. Let me change my together mode. Saya nampak together mode. Afsar, cuba you tukar scene dalam together mode ni. Sah, dah tukar scene belum? Dekat belah kiri bawah. Switch scene. Dalam together mode, itu tukar scene.
Oh. Saya tukar.
Tukar. Dah tukar belum? Amboi. Amboi ni kat dapur nampak. Lapar ke? Mentang-mentang saya lapar. Breakfast bagi meja makan. Oh, okay. Now I know. So in large gallery, even if I set my large gallery mode, not together mode, even if you change your screen as together mode, saya tak nampak. Tapi kalau saya as a host, I set myself as together mode, and you, any one of you change scene, saya boleh nampak. Okay, kita bagi plus. Siapa nak tukar scene? Kat tangan. Ni angkat tangan ni. Ya, dia bertukar lampu angkat tangan. Okay, cepat. Siapa nak tukar scene? I nak tengok. Kalau together mode, the bad thing is I could not see your name. Then I have to force myself remembering your face and your name. Fortunately, not yet achieving that goal. Siapa tukar sekarang ni? Anis Nur Azian. Change scene. Ni pun muka-muka lapar ni. Anis Nur Azian. Thank you for supporting me. I'm also hungry. I haven't taken my breakfast. So tadi tembikai. Sekarang kita makan banana. Anis Nur Azian juga. Alamak, dia nak berenang. Scuba diving kot. Ya. So I suppose yang senyum lebar ni Anis Nur Azian. Sekejap, saya tukar large gallery. Anis Nur Azian. Where are you? Okay, hi. Okay, thank you so much for your cooperation. So from today onwards, I also tell myself that I want you to be in class. So turning on your camera is compulsory throughout my lecture. But then I need you to make sure that you turn on your camera. If you don't, then I will remove you from class. How's that? Yeah, it will take some time. For your information, we will start our week 9 with topic 6. Topic 6 is not difficult, not to say at all tu macam lagaknya, but not so difficult, in comparison to the previous chapters and the upcoming chapters. Topic 6 tu masih lagi okay lah. You just need to focus on the theory and also the understandings of the principle. So I'm going to spend my time a little bit on checking every one of you before we start our doa. Dah termasuk agenda terlebih pula Ahmad Faiz, please raise your hand. Ni angkat tangan betul-betulnya. Ahmad Faiz. Nampak Ahmad Faiz? Okay. Ahmad Nazrin. Angkat tangan. Senang saya nak. Ahmad Nazrin. Ahmad Nazrin? Yes, Nazrin. Alah, kesiannya Nazrin. You baru bangun tidur ke? Mata you macam susah you nak buka tadi. Ahmad Nazrin. Angkat tangan. Nak tengok tangan you. Ada lagi ke tangan ni? Amira Fazlin. Yes, Amira Fazlin. Hi. Anis Nur Azian. Yeah, thank you, Anis. Atrisha, yes, Atrisha, thank you. Camelia. Yes, thank you, Camelia. Okay, Mashita, where are you? Yes, thank you, Mashita. Camera you turun bawah sikit. Your face is quite small, so tak puas tengok muka you. Mashita, thank you, Mashita. Mirza, thank you, Mirza. Yeah, happy eating your breakfast. Akasha. Hi, Akasha. Afsar. Mana tadi Afsar? Yes, Afsar. Azri. Yes, Azri, thank you. Hold on. Daniel. Daniel. Hi, Daniel. Oh, tinggi je. Osh. S1. S1. Hi, S1. Kamera you turun bawah sikit. Nak tengok muka you. Okay, baru puas. S1, thank you. Ya. S1, mana S1? Alamak. Sorry. Yes, S1, yes. Yeah. I'm talking to myself. Okay, Syafiq. Muhammad Syafiq. Alamak. Muhammad Syafiq berkod. Tak nampak lah nama penuh ni. Muhammad Syafiq berkod ni. Gambar profil dia ni. Muhammad Syafiq apa ni? Abdul Rahim. Muhammad Syafiq Abdul Rahim. Muhammad Syafiq Abdul Rahim. You're not responding. Oh, okay. Yang ni pun Muhammad Syafiq juga. Okay, Muhammad Syafiq. Yang ni Muhammad Syafiq apa ni? Muhammad Syafiq. Ya. Abu Hassan. Oh, dua-dua A juga. Muhammad Syafiq Abdul Rahim, thank you. Muhammad Syafiq Abu Hassan. I think you told me in the early class. What should I call you? Dua-dua Syafiq ke? Syafiq Abu, Syafiq Hassan. Abu Hassan, Almak itu nama sama. Syafiq Abdul Rahim, Syafiq Rahim, Syafiq Hassan. Okay? Jenuh saya nak ingat. Yes. Syafiq Rahim, Syafiq Hassan. Najwa. Raise your hand, Najwa. Thank you, Najwa. Nak kena scroll ni. Shadiana. Thank you, Shadiana. Syafiqah. Syafiqah, thank you. Nur Afifah. Afifah, thank you. Hi. Then I'm gonna click see more. Gila ni besar ni, Nur Afifah. Nur Alia. Raise your hand, Nur Alia. Nur Alia, where are you?
Ya, Profesor. Ya, Doktor.
Bila masa jadi profesor ni? Salah ni aku. Mana Nur Alia? Raise your hand, please. Tak nampak.
Yeah. Sorry, Madam. Sorry, Doktor. Tadi saya tak boleh open camera.
Oh, kenapa? Camera you? Something wrong?
Ya.
Kenapa?
Kalau start nanti dia blank.
Start until blank. So please seek help. Yeah, you know that the COVID cases is still thousands, 6,000. Semalam naik naik lagi. Yeah, I don't know how long will be our ODL it's going to be very unacceptable if you don't show your face in class. So I'm going to give you a chance sampai next week. Next week kalau you tak on camera, I'm going to remove you from class.
Alright,
Yeah,
Doctor.
because it's considered not present. You are not trying very hard to solve your problem. So seek help from, nak tengok sikit muka siapa yang ala-ala gamer ni. Azwan ni yang pakai headphone ni mungkin dia terror kot. You pergi tanya Azwan tu. Ada juga yang perempuan-perempuan dah pakai headphone. Ni Dania ni. Kalau dia pakai headphone tu agaknya dia gamer kot. Kalau dia tak score kelas saya siap. Okay, so you pergi tanya Nur Alia. Nazrin gelap besar main game Mana kerusi game you? So you pergi tanya orang-orang ni, apa masalah laptop you? So it's unacceptable if it's the third ODL, you still cannot solve your camera thing. It's a need at this moment. Wajib ada. Okay, wajibul gunnah. Okay, kat mana tadi? Nur Alia, Noreen. Yes, hi. Noreen, kamera tu turun bawah sikit. I tak nampak muka you puas. Barulah nampak. Alhamdulillah dari tadi ya. You makan breakfast ya. I dapat you kunyah je tadi.
Belum breakfast lagi, Doktor.
Alah kesiannya. Pergi ambil dapur, ambil makan. Saya duduk lepak-lepak lagi ni. Ashikin. Ashikin, raise your hand. Blanuren. Ashikin, tolong turunkan kamera you sikit. Kamera you. Screen you, I tak nampak muka you, nampak separuh pak hidung you tadi. Baru. Ni. You pakai headphone ni, Alia, you tanya Ashikin lah. Dia mesti pandai ni bab-bab laptop ni. You tanya Ashikin. Yeah, Fazlika, where are you? Raise your hand. Yes, thank you, Fazlika. Hi. Karya? Karya? Yes, thank you. Hi, Karya. Raja. Hi, Raja. Hi. Nornada. Nornada, hi. You tulis sikit you punya kamera tu, muka you tak puas lah tengok. Even though I know how you look like. Okay, great. Umaira, the last person. Umaira, where are you? Hi, Umaira. Okay, very good. So congratulations. So we only have one person who is not able to turn on the camera. Please seek help. I will give you till next week. Kalau you tak dapat solve juga, so I'm going to stick to my compulsory instruction because it's a discipline thing. Yeah. So kita dah 3 kali ODL, so we should try hard to make it possible. All right, very good. Congratulations to all of you. I'm going to screenshot. Smile, everyone. Smile. Thank you. Inilah semangat yang kita nak. Ya, I nak tengok skrin. I tak tengok skrin. 1, 2, 3. 1, 2, 3. Okay, I'm going to copy here. Selalunya sebelum ni kita duk guna emoji kan kat tangan. Rupanya puas lagi yang kat tangan betul. Sungguh-sungguh tinggi gitu. All right, very good. So we're going to start our class with the recitation of dua. I don't mind spending much time to do this. We are way behind from the agenda that I myself set, but I feel happy that we do this because it's very, very critical to make ourselves available in class, whereby I could see you, you could see your friends. Yeah. Now, we're going to start with the recitation of doa. So please someone volunteer for doa pembuka dan doa penutup, but every one of us recite our own doa together in between. Yeah. Who wants to try? Not try. Who wants to kejar pahala tu? Jom.
I guess no one.
Alhamdulillah. Akasha, thank you.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين حمدا يوافي نعمه ويكافئ مزيده يا ربنا لك الحمد كما ينبغي لجلال وجهك الكريم وعظيم سلطانك اللهم صل على محمد وعلى آله وصحبه وسلم اللهم اغفر لنا ذنوبنا ولوالدينا وارحمهما كما ربيانا صغيرا
Amin. اللهم اجعلني في قلبي نورا وفي لساني نورا وفي بصري نورا وفي سمعي نورا وعن يميني نورا وعن يساري نورا ومن فوقي نورا ومن تحتي نورا ومن أمامي نورا ومن خلفي نورا واجعل لي في نفسي نورا رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي.
اللهم افتح علينا حكمتك وانشر علينا من خزائن رحمتك يا أرحم الراحمين سبحان ربك رب العزة عما يصفون وسلام على المرسلين والحمد لله رب العالمين.
Amin, amin, ya Rabbal Alameen. Thank you so much to Mr. Akasha. So without further ado, we will start with our class. I hope you have downloaded the PDF for topic 6. I have uploaded it in class materials and files in your group, Microsoft Teams, and you should have it in front of you, yeah? If not, you just have a look at my share screen, yeah? So I'm gonna share my screen for the lecture. Kenapa dia ambil screen? I tak nak share screen, I nak share program. Apalah. Sekejap ya. Hold on. So can you see my screen now?
Yes, Doctor.
Right, very good. So we are now in lecture chapter 6, or in other words, topic 6. We are still going to use our Fogler 2016 and also the 5th edition. If we have 4th edition, it's okay. I already start using the 5th edition for the upcoming chapters. For this chapter 6, I still refer to the 4th edition. Yeah, so get ready. If you have the 5th edition, very good. But if you don't, then it's still okay. It's just a rearrangement of the chapters. Yeah, we will also be using the Lebensspiel 1999. Some of it, some of the contents that we have for topic 6 today are also taken from Lebensspiel. Now, so these are the sekejap. My usual problem, preparing my pen. Okay, so this slide shows you the topic 4, then topic 5. So we have learned about the chemical reactor design, the design of ideal reactor for single reaction. Yeah, single reaction. And you have been tested for your midterm assessment for from topic 1, 2, 3, and 4. Then we have learned right before the midterm assessment, our topic 5. You haven't been tested on the topic 5 anywhere, but you could see that some of the questions given for the assignment, your take-home assignment, are taken from topic 5. Yeah, so you need to know which questions referring to topic 5. You haven't been tested in midterm assessment, yeah? So topic 5 now currently given as assignment. And now we are going to start with our topic 6. And we have many parts, 1, 2, 3, 4. Today, I suppose we will try to finish part 1 and part 2. Yeah. So let's start with part 1. So this is topic 6. Again, we will still be learning about the chemical reactions, but notice the word that we have here is the multiple reactions. So focus, we will be looking into many equations at the same time in a reactor. So the few things that you want to know when we have many reactions simultaneously or in series or in parallel or whatever, reacting in one pot or in one vessel or in one reactor, we need to know our target. So we need to be selective. So that is why we have to identify the selectivity, and of course out of the products produced from the reactant, since many reactions, so we need to know our yield as well. Yeah. From there, we can also make our choice depending not only on the selectivity of the products, many products produced from many reactions, the multiple reactions. We also want to design our best reactor selection according to the understanding of the selectivity and also the yield. Here we will also look into the series and parallel reactions which are occurring at the same time in one vessel, because we are talking about multiple reactions. Due to that, we also look into further complexity, complex reactions, so we call it complex reaction. Yeah, so you may ask, what does it mean by selectivity? Yeah, the key word is we want to select what is the product that you want, yeah, out of the many products. So we call it desired product and the undesired product. So you need to know to identify which is the desired product and which is the undesired product. Yeah. So again, I put here as the F, G, Fogler, LS, Levenspiel, and chapter. So you could, if you have your textbook, I would recommend you spend your time, anytime, to also look through your textbook. Yeah. It's much better if you read from the textbook as well, rather than listening from me. I may skip some things. I may explain not thoroughly. So to enhance your understanding, please also read your textbook. All right, so the multiple reactions, meaning we may have many reactions producing desired and the undesired products. So for the desired product, it comes from the desired reaction, and for the undesired product, it comes from the undesired reaction. So there are four kinds of multiple reactions discussed in this topic 6, which are series, parallel. You have seen that from our previous chapters on the series arrangement of reactors. So we are talking about reactors which are arranged in series, or reactors which are arranged in parallel. Yeah, if you don't remember now while we are talking at this moment, so make sure after class flip back your chapters and try to enhance your understanding. What is series arrangement? Yeah, what is parallel arrangement of reactors? But in these chapters, we are talking about series reactions, the equations, and parallel equations in one reactor. So it's somewhat different. And we also identify some of the reactions, the multiple reactions, as independent, and lastly, complex reaction. And talking about that, the desired and the undesired, so we'll write D, capital D as desired, and capital U as undesired. Yeah. We are going to identify this or quantify this based on selectivity parameter, yeah, together with reactor selection and proper choice. So you have to make a choice. Which operating condition? Operating condition means which temperature, which concentration, which pressure, yeah, for your reactor choice, yeah, the operating conditions in order to minimize. So our target is to produce as low as possible the undesired. Yeah, of course, the undesired, in other words, we call it as the byproduct maybe, or maybe the main product from the other reactions, but we don't want that relatively to the other product. Yeah, so we want to minimize the undesired, or we call it as the unwanted side reactions. So your target is, how are we going to do that? Yeah, finally, you are the engineers who are going to propose the reactor designs or the arrangement of the reactors to your chemical companies. So you need to know this basic understanding first. So this slide, the 10th slide, shows you the many kinds of reactors which you have learned before. Yeah, the batch, CSTR, plug flow, either series or parallel, back to back. We don't really look into pad back, but inside this vertical column, we have packings. Yeah, and that packings are the packings contain catalysts, for example. Yeah, so we don't really look into this, but I still have to mention this because in industry we use lots of these back reactors. Yeah, for a reason, to easily separate the catalyst out of the, let's say, liquid or gas. Yeah, the catalyst will reach its maximum shelf life, so we have to regenerate it. So easily we take out the packings. Yeah, then we substitute it with the new packings containing the same catalyst. So that is why it is muchly used in the industry using the packed bed reactor. Yeah. Then we also have the combinations of the reactor arrangement, either with the CSTR together with the PFR, how you arrange it in your topic 5, either PFR first or CSTR first or whatever, yeah? Okay, so out of the all the kinds of many different modes of reactors, of course, it produce the products, yeah, either the desired or undesired. Then you need to go through separation to separate between the desired and the undesired. So in chemical engineering industries, we call the from the separation towards your right is your downstream processes, yeah, and towards your left would be your upstream processes. Yeah, this is basically the simple definition for chemical engineering industries. But if you look into the overall industry, starting from the oil and gas, drilling and so on, then the drilling part, yeah, the offshore part is actually the upstream, yeah. Kalau orang oil and gas, dia kata lepas dia dah drill, dah dapat minyak tu, from there onwards, dia dah kata dah downstream. So kalau, so you have to know who you are talking to. Kalau you are talking to people from oil and gas, engineer dekat offshore tu, bila you cakap downstream start daripada separator, dia kata, tak. Maksud saya downstream tu start daripada kami bagi you minyak, tu downstream lah. Iaitu dalam reaktor tu pun dia kata downstream dah. Yeah, but if you start from your chemical factory yang memang untuk produce your product, starting with your reactor, so your reactor starting until your product here, until here, before you start to separate, that is your upstream. Okay, all right. Okay, so we're gonna go to the main contents. Yeah, we're gonna look into either parallel, series, complex, independent, or potpourri. So this is taken from Levenspiel, yeah, and additional information on the multiple reactions. It's very interesting, so you may want to look at that as well. Yeah, so let us start with parallel reactions. So for parallel reaction, if you notice, we have the A as your reactant going through two pathways at the same time in parallel produces two products, B or C. So your right-hand side shows that we have two pathways. One pathway having the complete combustion producing ethylene oxide from ethylene. The other one at the same time, ethylene also going through another pathway producing carbon dioxide and water. Yeah. So the reactants are consumed by two different pathways to form two different products. So we call it competing reactions. Okay. And it's a parallel reaction. All right. So let's go to the next slide. Series. In comparison to parallel series, we start with the A as the reactant, going through the first pathway with the first rate constant K1 producing B, and from that B, it produces C with the K2 rate constant in a second pathway. So in between, you have B before it produces C, you call it as intermediate product. So this is what you see from, I think, your assignment. So one of the assignment, it mentions about intermediate, yeah? Intermediates and also radicals, yeah? So it's maybe it's new to you, but it is not so new. The question asks you to calculate your volume, but it uses the complex reactions, yeah? So try to selami daripada hari ni you belajar dan you bolehlah buat you punya assignment tu, yeah? Alright, the reactants forms an intermediate. So the intermediate is the B in a series reaction, then later produces another product, which is your end product, C. So the real example would be the ethylene oxide as your A, finally produce TEM, triethanolamine, and your intermediate is DEM, diethanolamine. diethanolamine. So how you want to pronounce it, okay? Okay, so it's a series reaction. For the real example here, why is it series? Because we have this ethylene oxide as your A, then it produces monoethanolamine and also diethanolamine as your intermediate, yeah? And finally, from your intermediate, it produces your C, which is your TM. Okay, now let us go into much complex reaction. These are multiple reactions. We have two kinds of reactions here. The A plus B produces C plus D. Yeah, in a series reaction. Why is it called series? Walaupun dia ada parallel dua, nampak parallel, it's a parallel combination with series as well. Why? Because we have reactant A and B react with each other to produce C and D. And that C is used in your second reaction. So ibarat macam dia sambung. So it's a series reaction. But at the same time, in your second reaction ada A. So dia dah jadi parallel. So it's a combination of both the series and parallel reactions. So we have couple simultaneous. The reactions run or happen simultaneously in series or in parallel. All right. So these would be your real examples. So we're going to go to the next slide. You could see it much better. We're going to use the example of ethanol. Yeah, ethanol produces ethylene. Ethanol produces ethylene and acetaldehyde. Yeah. Okay, so it's a simultaneous series reaction. So we have ethylene and acetaldehyde. So this ethylene and acetaldehyde reacts with each other to produce butadiene. All right. And that ethylene and acetaldehyde are considered as intermediate before we finally produce our final end product, which is butadiene. So it's a simultaneous series reaction. Okay? Any question? Do you have any question? Okay, so we're going to go to our next slide. If you don't, I'm going to go to our next slide. Independent reactions. Tadi dalam when we are producing our end product, we got intermediate, and producing that intermediate, kalau series, maksudnya from the previous reaction, is also used in the next reaction to produce our end product. Yeah. If parallel, then we have simultaneous reactions producing two different products. Now, if we look into independent reactions, why we use this word independent? So let us look at the definition of the word itself. Yeah, a reaction that occurs at the same time, but neither the products nor the reactants react with themselves or one another. So we have reactant A produces product B plus C at the same time. The other reaction in the same reactor, D produces E plus E. So B does not react with D, yeah, to produce E and F. Yeah. So A does not react with B and C. B does not react with E and F. Yeah, so dia tak react. Dia produce asing-asing. So E jumpa B, okay, hi. Dia tak produce another product. Yeah. C jumpa F, okay, hi. Okay, tak compatible. So dia tak boleh produce something like that. Bahasa bodoh-bodoh. Yeah, so this is what it means by independent reactions. So we have this cracking of crude oil to produce gasoline as your real example of independent reaction. So we have your crude oil producing dodecane and propene, and we have simultaneously in the same reactor, we have the octane, which is the gasoline from the crude oil, producing hexane and also ethane. Right? I hope, tak ingat kamu semua ni daripada matrix kan? So maybe I'm not sure whether you have learned about this cracking of crude oil somewhere. Have you? Have you learned about this cracking of crude oil somewhere? Tak ada eh? Okay. Even if tak pernah ke, please after class, tengok. Kalau you tengah boring ke dalam kelas ke, you pergi survey-survey, tengok cracking of crude oil. You may understand what it means. Yeah? Alright? Okay. It's very important you faham cracking the crude oil. In the crude oil itself, ada banyak Cs. Cs tu bila saya sebut C itu masuk carbon. Carbon as a component. C1, C2, C3, C4, C5, C6, blah, 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 blah. Ada banyak six, so it has to be cracked, yeah. In an equipment, yeah, cracking, yeah, the crude oil, producing hexane, ethane. So these are hexane, C6, yeah, ethene, C2. Then we have C12, yeah. So we produce all many Cs from the cracking of the crude oil itself. So that is why petroleum is still very expensive, yeah. So sebab itulah orang tergila-gila kejar petroleum ni at the moment until we exhaust the crude oil lah. Alright. Now, we're going to go to the last part of the first multiple reactions example, which is the potpourri. Potpourri tu bukan yang fragrance yang dekat meja you tu. But this one, why is it called potpourri? So let us look at one by one. So we have many kinds of potpourri of multiple reactions. Saja je dia panggil potpourri because ada banyak dalam tu, ya. The multiple reactions. For example, we have series. Kalau series sebelum ni, if we look into series, A plus B, A produces B if it's isomerization, or if it's not, A plus B produces C. C pula produces something else. So ada dua layer je, dua pathway atau two rate constants only. But here, if you look at this potpourri, banyak dalam tu. So we have many case lah pula tu. Case. So A produces R, R produces S, S produces T. Mungkin ada other complex multiple reactions yang produces other end products. Some more. Secondly, we have series parallel, or we call it consecutive comparative. So it's very comparative. It's competing between each other because we have intermediate. So please now, if take note, yeah, of the keyword intermediate. When I mention intermediate, you can ingat, nanti dalam ada multiple reaction yang produces intermediate. So if I ask someone, Amira, untuk series parallel, give me the example of intermediate dalam ni. Amira.
B.
Yes, very good. B. Some more? B itu intermediate ke? B tak intermediate.
R.
Intermediate means, yes, very good. So we have R. R is the intermediate, yeah? So the intermediate always refers to the product. After that reaction, you produce product, and that product will be used as reactant in another reaction. B ni tadi, dia memang asalnya reactant, ya. Dia bukan intermediate. So it's there. In the same reactor, dia ada A, ada B, then the A and B react, produces R, and then the R reacts with B, which is already in there as reactant. But the R is the intermediate, yeah? The R and B react with each other to produce S. S the intermediate. Bagi jawapan pula laju pula. Alah, nak tanya soalan pun terlepas tadi. Tak apalah, sambung. So the S is the intermediate, and now the S react with B, which is originally as your reactant. Okay? All right, very good. So, reversible. So we have reversible. So I'm going to ask someone, Nazrin, what can you say about reversible reaction? Garuk kepala dulu kan, Nazrin? Kita tengok yang this example. Reversible. Cuba bagi tahu saya sikit apa yang you faham about reversible. Mike. You tak jawab, I kick you out. Mana Nazrin ni? Kick you out. You tak jawab. Nazrin. Cepat. Lambat betul saya nak cari nama Nazrin ni.
Tak pasti tu.
Okey, walaupun you tak jawab tak pasti, maksudnya I tahu you dalam kelas I. Tak jadilah kick out. Okey, tanya Azri. Azri, you punya kamera tu turun sikit. Baru nampak muka you, tak ada nampak hidung je. Okay, Azri, what do you understand about this reversible? Cakaplah apa-apa you faham selama ni.
Reversible reaction like apabila reaktan jadi produk and produk tu boleh jadi reaktan balik.
Faham pun. Tapi can you express it in English?
The reactant when the reactant produce a product, and then a product can be able to return back to the reactant.
Okay, very good, Mr. Azri. So I would like to enhance the explanation. Thank you, Mr. Azri. The A produces the R with a certain rate constant. So we call it Ka, the rate constant, positive. Ka, the forward rate constant. So who wants to sambung? Who wants to continue? Siapa kamera dia paling kecil, dia yang kena. Syafiq. Syafiq apa benda ni? Syafiq. Syafiq yang kamera kecil. Syafiq tak pakai headphone. Syafiq Hasan ke? Syafiq, sambung.
Saya ke?
Mr. Syafiq. Yes.
Oh, okay.
Okay. So we talk about A produces R with the forward reaction with the rate constant Ka. So how are we going to express that in a reverse reaction?
Negative Ka.
Yes. Negative K. Okay, dia dah jawab, tak apa. Kita bagi Akasha. Akasha. Negative K betul ke?
Negative KA, Doktor.
Betul ke negative KA? Adis. Adis Azian.
Ya.
Yes. Betul ke Akasha jawab negative KA? Reverse reaction. The rate constant.
Maybe not.
Maybe
Yes.
not. So what is the not maybe?
I'm not sure.
Okay, very good. You're not going to be kicked out, not sure. Nor nada. Oh, nak pula ya. Gugur nak kick out dia rajin tu jawab. Nor nada.
Ini jadi negatif KR kot. Negatif KR. Ataupun KR je. Kalau dia
Negative
reverse
KR.
from R to A lah.
Okay. Saya nak tanya siapa pula. Okay, belum tepat lagi. Noren. Yang lain-lain tu flip lah. You punya lecture notes. Yeah, because our upcoming chapters, we're going to look into many reactions of reversible. And in industries, they are very common to be dealing with reversible reactions. So your fundamental understanding must be at your fingertips. Noren dengar ke kita panggil dia ni?
Dengar.
Noren.
Saya tengah ni lecture notes.
Yes. So ada jawapan tak?
Kejap
Yelah.
dah tengah cari.
Tengah cari, okey lah, tak kena kick out, dia jawab, saya dengar suara dia. Okey, nampak muka bersemangat tu, Najwa macam serius, dia baca lecture notes, Najwa. Dia tengah mencari dekat skrin tu, serius dia duk flip lecture notes mana. So I'm gonna make it fast. So I'm gonna ask you more questions in our next slide. So kat sini, if you go reverse, so we call it, if we normally write it with respect to our limiting reactant. Always take note, yeah, limiting reactant. So we consider the A as the limiting reactant walaupun dia tak ada B kat situ. So it's an isomerization maybe, but it's a reversible reaction. The forward rate constant is Ka. If you still write it with respect to the limiting reactant A, so we write it as K minus A. Betul ke? Yeah? And then you do the same to that, Kr, then K minus R. Then out of that reversible reaction, we know that the rate constant is the small k. But when we have reversible reaction, it reaches certain equilibrium. Yeah. With that equilibrium, bila that equilibrium is dikacau due to the concentration changes, then according to the Le-Chatelier principle. So take note, Le-Chatelier principle. Siapa yang tak pernah dengar, please you belajar kot dalam you punya thermodynamics. Pergi tengok balik teori you Le-Chatelier, disebabkan that Le-Chatelier principle, dia pun pergi forward ke dia pergi reverse. Yeah, so please have a look into that. Is the main principle, basic, and you should have it at your fingertips before we even go further into our reactor designs. You engineer, kerja you design. Tapi kalau you tak faham, if you don't understand the fundamental principles, then you may design it wrongly. So this is what we do in our topic 6. From our understanding, we have to make decisions. Which reactor selections would be the best reactor, yeah, for that, for your productions. So we go to the next one, reversible network. So it's a network A, reversible producing R, and A at the same time producing S, and R producing S as well at the same time. So it's a network. Then we have reversible and irreversible. So we have reversible reaction and we have irreversible reaction. Then we have then B system. So the A irreversible producing T and A at the same time irreversible producing S, S irreversible producing S, U, sorry, and also S. All right. So this is why we call it as a potpourri multiple reactions. So you can have a look at further details in Levenspiel. Now we're going to go to the basic business, main business, desired, undesired, instantaneous, and overall selectivity. The key word here is selectivity because we want to select between desired or undesired. We only want to focus on producing more of the desired and producing as less as possible the undesired. Yeah. So when we want to do that, we have to do the quantification based on formulas. So there are two kinds of formulas of selectivity. One is instantaneous and the other one is overall. So we're going to go into that further after our first break. Okay. So let us take our first 5 minutes break. Aizwan tu, saya baru macam ni dia dah mengelak dah. Alright, very good. So let us take our first 5 minutes break. Thank you. Kita juga. Kita beri tahu dah dapur. Okay, Assalamualaikum warahmatullahi wabarakatuh. You should now be at your own seats and I should be able to see you. Okay, Mr. Raja, where are you? Okay, very good. Ashikin, very good. Very good. So we're going to make this as our common practice. So 2 minutes before we're going to take our 5 minutes break. Then we're going to spend 2 minutes to prepare ourselves on our own seats and with your camera on. Yeah. So in between, of course, I will call names. Now you could still see my slide, right? Could you still see that?
Yes, Doctor.
Thank you, Mr. Akasha. Right, I'm going to go to our next slide. Oh, sempat buat air Akasha. Air sejuk ke air panas?
Sejuk, Doctor.
Oh, sejuk ke? Sejuk paling cepat sekali ya. Alright. Okay, we're going to go to our next slide. Hold on, benda ni kacau saya tak nampak. Okay. Desired and the undesired product. So we use D, the capital D for the desired, the capital U for the undesired. So we have this example of reactions, parallel reaction of A producing D with the rate constant. Now the rate constant is referring, so we use rate constant with respect to the desired. Yeah, in this topic, we write the rate constant based on the desired, yeah, not based on the limiting reactant. Okay, please take note. So it's just a notation that we use in order to show the rate constant influence when we do our reactor selection, okay, based on the desired product and also the undesired. So we have another reaction which is in parallel producing U, which is the undesired. So with the rate constant with respect to the undesired. So we have KD with respect to desired, KU with respect to the undesired, and the K is the specific rate constant, yeah, based on the D. The first one, KU, based on DU. All right. So we also have this example of series reaction, A producing the desired product, and that desired product unfortunately can go through a irreversible reaction producing the undesired product. So the desired product is in between, yeah. We have KD, the rate constant with specific rate constant with respect to the desired in the first reaction, and KU is the specific rate constant with respect to the undesired product. So our target is to maximize the production of the D and minimize the production of the U. So how do we do that? Yeah. So your role is to choose or make a choice of the best operating conditions and also reactor. Yeah, there are many kinds of reactor that we can use to cater the fundamental objective, yeah, in order to allow producing as much as possible the desired in this series reaction or parallel reaction, this one D, and to minimize the undesired. Yeah, so this is our problem statement. that is the nature of the reaction itself. Ya, dia boleh produce pula benda lain, ya. So as scientist dia bagi tahu kita je, okay, ini akan berlaku. As engineer, okay, thank you for the information, scientist. I think we can handle this. You pun jawab. Oh, scientist pun macam heran. Macam ni boleh handle? I buat dalam lab dia duk produce dia undesired. Dia tak panggil undesired. Tapi you as the engineer for your production, you tahu, tak nak ni je. Yeah. So that's where you use your fundamental understanding in reactor design, yeah, to only produce the D. So now, the next slide, we're going to go into the efficiency of the reactor. Yeah, when we do our design, we may choose specific design, and when you have that reactor chosen, you also need to elaborate or investigate the efficiency of the reactor. Yeah, why? Because we are dealing with the cost. Yeah, so we have the y-axis as the cost, the x-axis as the either high efficiency if you go to your right, or low efficiency. Yeah, so we have many parameters to look into on the cost, either the reactor cost. So this is what you're going to do in your final year. You buat kira-kira size banyak mana based on your chemical engineering design, your mechanical engineering design, and finally you kira duit. Yeah, the cost to design as such reactor, and also the separator cost, the same thing. And considering both reactor and separator, we look into the total cost. Of course, the total cost in this chapter, CHE502, reaction engineering, dia cuma cakap reactor and separator je. But in reality, when you are in your final year, the total cost is not only the reactor and separator. Banyak lagi benda lain lagi. Yeah, auxiliaries, your heat exchange equipments, your other kinds of equipments in preparation for your reactor, and so on. Your pipings and many more. All right. So please take note in this chapter, since this is referring to reactions in reactor. So total cost tadi kita the reactor cost, and now we relate it a little bit more on the separator cost. So you know, as the efficiency goes higher, the reactor cost would be higher. But with the efficiency, a higher efficiency, because you produce as much as possible your desired product in your reactor with high efficiency, of course you have to spend a little bit more of money there. So your separator cost becomes lower because your desired product tu lagi banyak daripada your undesired product. To separate the desired product from the undesired product, which is at its minimum, needing not as much complex separator equipments. Yeah, so this is what it means. So if you go to your next slide, ni saya untuk mengajar, saya buat sini kosong lah. Dalam lecture notes tu you dah dapat dah jawapannya. So you could see the relationship between the efficiency. When you have high efficiency, you need to spend more money. Since more of the desired product, so separation lesser complexity, so the cost for the separator is lower. But if your efficiency of your reactor, you choose inefficient reactor, so it produces more of the undesired than the desired, then of course you tak spend so much money for that. Yeah, happy, seronok. Tapi if you go towards your downstream processes, you have to separate many series of separator because susahnya nak separate, something like that. So you have to spend more money on the downstream processes. Yeah, so you should be in between, yeah, balancing between the cost during your upstream processes to your separate downstream processes. But rule of thumb is, if the reactor cost is higher, yeah, of course, more of the desired, then the separator cost is lower. All right. Now, so this is what happens in your reactor, having your multiple reactions, producing your D and also your U from your reactant A, for example. Yeah. So in your downstream processes, you may want to use distillation, katakan, atau separator. You want to separate between the desired and the undesired. So how are you going to tell that to explain that in reports? Yeah, quantitatively explain this. So there is overall S, which is S bar, and instantaneous S, which is only S. And each of the S is the selectivity. We have S bar with respect the desired with respect to the undesired. The instantaneous, the same thing, the desired with respect to the undesired. So we're going to look into what is the difference between the overall, which is the S bar, between the S bar and also the S. Now, so this is instantaneous selectivity, which means the rate of formation of the desired divides by the rate of formation of the undesired. Logically, if I ask you, Faiz, from this reaction, from this equation, the instantaneous selectivity, all right? How, because you nak, target you nak produce desired, right? What would you do to have high instantaneous S, Mr. Faiz? Mr. Faiz, Ahmad Faiz Abdul. Kalau you tak jawab, I remove you from meeting, nanti you masuk balik. Remove. Masuk balik. Seronoknya. Azri. Gelak ya, gelak. Azri. Back to my question. How to have high S from this equation?
To obtain as we need to increase the rate of formation of D.
Yes, very good.
And decrease the rate of formation of U. Then we get the height S.
For the rate formation of U, you kata decrease ke increase?
Decrease.
Very good. Thank you. Jom tepuk tangan. Alright, very good. So I'm going to go to our next slide. Very good. Tolong bagi tahu Ahmad Faiz. Jangan kecewa. Masuk semula kelas. Kenal ke? Siapa kenal Ahmad Faiz? Tolong bagi tahu dia. Saya tak rasa bersalah, okay? Tapi dia yang nanti kecewa, depressed pula. Okay, so we go to our next slide. So we have this S bar, yeah? Take note that we have that symbol at the top of the alphabet S. It's S bar. The S bar refers to the overall selectivity. So the formula is simply the flow rate of the desired divides by the flow rate of the undesired. All right. So the other words, you know that the flow rate is also defined as the rate of formation of the desired times the volume. Yeah. Same goes to the flow rate of the undesired, the rate of formation of the U times the volume. Okay, mana Ahmad Faiz ni tak masuk-masuk lagi? Kecewa ke? Ni lah masalah pensyarah ni. Konon nak strict, lepas tu rasa bersalah pula. Mana si Ahmad Faiz ni? Kalau tak masuk, tak nak forward. Tak nak proceed. Dia bagi tahu cepat. Ni my common practice ya. You kena keluar, lepas tu you masuk balik segera. Selagi dia tak masuk, I tak go forward. I tak proceed. Mana dia? Mana dia Ahmad Faiz? Okay, bagi lagi sikit masa. So we have this S bar. For the batch reactor, yeah, for the flow reactor, it's the ratio of the flow rate, yeah, exit molar flow rate. For the batch reactor, remember in batch reactor, we don't talk about the flow rate because batch reactor is simply the batch. Tak ada flow in, tak ada flow out, yeah. So we have this ratio of the number of moles, yeah, S bar overall. All right, so we're going to go to our next slide. Now, this is simply the proving, yeah. Ini hanya untuk practice you punya understanding, yeah. We're going to say that the S bar is actually equivalent to the S. The overall selectivity is equivalent to the instantaneous. So those are the steps for you to prove that the S bar, which is the flow rate formula ratio, is equivalent to the instantaneous selectivity, which is the rate of formation ratio formula. Okay? All right, so we're going to go to our next slide. Now we're going to look into two other parameters example, which is the instantaneous reaction yield, based on the desired with respect to desired and overall. So we have Y here. Simbol kat atas tu adalah apa? Ingat mathematics you. Ingat mathematics you. We have this Y what? What do you call that symbol above? Ingat tak? Ingat tak ingat? Okay, for the here, the bar, we call it S bar. The overall selectivity. Then the yield, we have the Y without the symbol above it. So we have this symbol, we call it tilde. Tilde or DA ke DE ke tak sure. Tilde. So Y tilde. So when I say Y tilde, it refers to the overall yield. Y tilde. Okay, Faiz, you are back. Please raise your hand. Okay, now we're going to look into the instantaneous and overall. So these are the two equations that you already see in CSTR, the rate of formation of the desired and also the undesired, and the flow rate, the molar flow rate at the exit, yeah, at the exit, keluar daripada reactor tu, of the desired and also the undesired. So now we're going to look into the yield. So Y, which is the instantaneous reaction yield, refers to the rate of formation with respect to the desired divided by the rate of disappearance of the reactant A, the limiting reactant. So A always refers to your limiting reactant or your key reactant. In this case, it says key reactant. So normally the key reactant refers to your limiting reactant lah dalam reaction yield. Limiting reactant yang habis cepat tu lah yang critical sekali. So minus RA, yeah. The rate based on selectivity and yields give insights on choosing your reactors. So that's why before you choose your reactor, you have to cater all possibilities of the theoretical understanding based on you nak apa? You nak produce yield. You nak yield you tinggi. Yield apa? Yield of your desired product. Yeah. You nak apa? You nak make sure that your reaction keluar tu produces more of the desired rather than the undesired. So be selective. So a balance between your conversion, a balance between your selectivity, a balance between your yield is also very important. Sebelum ni you belajar conversionnya, capital X. Alright, conversion. Now, in multiple reaction, not only conversion, you have to choose, you make a choice. Which selectivity value yang most optimized, all right, in comparison to your yield. Now, we're going to look into the Y tilde, the overall yield, which is simply the number of moles at the end of the reaction of the desired divides by the initial number of moles of your key reactant minus the final or remaining. So this refers to your remaining, okay? And A is your remaining key reactant. Initial minus remaining, which is no, not remaining. Initial minus your final A, remaining lah, remaining A. So that would give your Y tilde, overall yield. Okay. And that is for batch. If you are referring to your flow, the Y tilde in flow, so rather than using the number of moles, so we use the flow rate, the exit, flow rate yang keluar for the desired divides by the outcome of the initial flow rate. Kat sini initial flow rate, FA naught, keluar ni FA, ya. The FA naught minus the FA, yeah, that will be your overall yield. Very good. So we're going to go to our next slide. Now, so this is the real business. You already know that you are being selective. You want to have high selectivity, konon-kononnya, the desired product with respect to the undesired product, but you are in dilemma. Which one would be your main choice? Higher selectivity or higher conversion? All right, so which one to choose? So normally, greater conversion achieved of the desired would also give, because this is multiple reaction, would also give higher production of the U. Yeah, so that is why you ada dilemma, because we have multiple reactions. Satu reaction produce the D, satu reaction produce the U. Yeah, so if we have high conversion for both, because we have two different reactions, so you are in dilemma. Both of them with high conversion would give you high D and high U. So that is why we have this selectivity. Nak kena select lah. So the challenge the challenge is still there to increase the conversion, but we want to, of course, we are not going to say, alah turunkanlah conversion. We are not going to say that. We are going to make it a balanced situation, still high conversion, but with good selectivity, whereby you have less undesired and high desired. Yeah. So when you do your chemical engineering design, not only talking about the conversion, you would also need to justify your selectivity. Now, that would be the end of the part 1. So we're going to proceed as fast as possible to part 2. So we have parallel reaction from one reactant or two reactants. Going to start with the from one reactant in a parallel reactions. Now, we have parallel reaction. The A produces the desired. And another reaction, the A produces the undesired. Of course, in each of the reaction, we have the rate of reaction equation. So the rate of formation, in this case, since we use not minus R based on limiting reactant, but we use based on the R with respect to the desired. Yeah, in this case, rate of formation. Yeah, rate of formation of the desired product. And in reference to that, rate of the formation of the undesired product. So do not get confused from our previous chapters whereby you write your rate of reactions based on the disappearance of your limiting reactant. Yeah, so you use minus RA. Okay, in this case, of course, we still use that minus RA. Yeah, the rate of disappearance of the key reaction is the combination of the rate of formation of the desired plus the rate of formation of the undesired. You still use the basic equation of the rate constant of with respect to the desired times the concentration. So remember, we have these two parameters, the rate constant and also the concentration. If you say it's elementary, then the concentration of your A is to the power of the order of the reaction. If it's desired, so the power of, it's the order of the desired reaction, alpha 1. Yeah. Undesired, alpha 2. So we have this alpha 2 for the undesired. So simply add those up and arrange that in your selectivity, instantaneous selectivity formula, which is the ratio between the RD over the RU. And finally, there is your final equation, having your rate constant, specific rate constant, with respect to the D and also with respect to the C times the concentration, yeah, delta C. Because your power is the desired and also the undesired, alpha 1 minus alpha 2. So let's go to our second case, two reactants. Two reactants means we have A and B, both different reaction producing D and C. Okay, so we're going to arrange that. Rate of disappearance of the key reactant. Of course, this is your key reactant, meaning limiting reactant. Simply the addition of the rate of formation of the desired and undesired, rearrange it, and finally you obtain your instantaneous selectivity. Okay, with that formula. All right, we're going to go to our parallel reactions again, but from one reactant and two reactants. So this is not again, yeah, we're going to go, we are going to look into the summary, yeah. So the instantaneous selectivity formula for the first case and instantaneous selectivity formula for the second case, yeah. Whereby this one, the first one is for one reactant, the second one is for the two reactants. Two reactants here, one reactant only. Both producing the desired and the undesired as shown on the slide. Okay. So how to increase the instantaneous selectivity, your selectivity? Of course, you want to maximize your desired and minimize your undesired. You already answered that. Tadi saya tanya siapa tadi? Azri ya? Azri jawab, reducing your rate of formation of the undesired would give high selectivity. Okay? So now, this is the real business of the engineer. Ya? Kita dah tahu dah, kita nak maximize our desired product. So what do we do? Okay, simply adjust the reaction concentration. Which concentration? So we're going to look into that in detail. Or we could also choose proper reactor. So the question is, you nak buat dua-dua ke you nak buat salah satu? It should be dua-dua ke salah satu? Afifah?
Dua, Doktor.
Okay, Akasha dah jawab. Dua-dua. Selamat, Afifah. Alright, thank you, Mr. Akasha. Of course, you kena buat dua-dua lah kan? Yeah, so we're going to adjust our concentration. But how to adjust it? The next question is how to adjust it. Ikut suka selambarok. No, we're going to adjust the concentration based on our theoretical understanding. Yeah. Then, of course, you do that best with the right reactor. Okay. So we're gonna look into different cases lah. In that case, we have the selectivity equations, and we are going to simulate different conditions. Yeah. And that simulation based on different cases. We have case 1, 2, 3, 4. How do we simulate that? Simulate tu maksudnya kita we foresee different scenario. Siapa suruh? Sendiri buatlah. Sendiri foresee possibility of scenarios. So we distribute that into case 1, case 2, case 3, case 4 with that conditions. Yeah, the first one, alpha 1, if you go back to our previous slide, the alpha refers to the order of reaction. And here we have alpha 2, either alpha 1 greater than alpha 2 or alpha 1 lesser than alpha 2. That is the scenario that bukan saya buat, because that is the possibility scenario could occur, yeah, in any incidents or happening from your reactions. Case 3 and 4, we're going to compare or simulate the situation whereby the selectivity also would be influenced by the activation energy, yeah, of the desired or the undesired. All right. So why this condition occurs? Because we have Arrhenius equation due to changes of temperature. The temperature may change during your reaction. Kenapa? Because we have two different conditions, either exothermic or endothermic. So the temperatures changes due to that reaction. The temperatures changes, so the activation energy may also change. The rate constant may also change. Yeah, so those are the theories that you have learned before in our previous chapters. So we're going to simulate, let's say if that is the case, so which reactor system or which concentration, based on that scenario, which condition should we choose as our choice of selection? So let us look into the first case, which is the next slide. This slide shows you the overall symbol that we have. Alpha 1, alpha 2, the instantaneous selectivity, the activation energy of the desired product, undesired product. So please take note of the unit. Always, engineers, they refer to unit. Yeah, bila you tulis your order, of course, do unit. The selectivity, the ratio, cancel out unit, no unit. The activation energy, it's either joule per mole or calorie per mole. Then we have the specific rate constant. The unit depends on the alpha. Of course, you remember that we do that in our first topic, second topic macam tu, when you write your units of your specific rate constant changes based on first order, second order, zero order, third order. Yeah, remember that? Then we have your concentration of your component A. Yeah, concentration is always mole per liter, so the liter is written as meter cube. Yeah, 1 meter cube is equivalent, 1 cubic meter is equivalent to 1,000 liter. So this is mole per 1,000 liter. All right. Gonna start with our first case. If alpha 1 is greater than alpha 2, okay, for one reactant A in a parallel reaction. Now, this slide shows you we have parallel reaction. The first reaction producing the desired, the second reaction producing the undesired. So we know our selectivity. So that is the equation. And from that equation, we make assumption. Yeah, the assumption is made because we want to simplify our theory. All right. Let's say the alpha 1 is greater than alpha 2. And we represent the alpha 1 minus alpha 2 as A. All right. So the outcome from that difference formula is A is greater than 0, meaning positive value. Meaning kat sini positive value. All right. Positive because alpha 1 is greater than alpha 2. So our equation, the final equation for the selectivity now becomes that equation. Ca, take note of the concentration. Ca is now, Ca of reactant A is now with the order of, with the power of A. The order of reaction is A, yeah, A. So from that equation, we say if we want to have selectivity, instantaneous selectivity, which is high, must be high. Of course, we want high. So from that equation, the Kd must also be high. Ku must be low. Then only we can get high selectivity. So that is mathematical understanding, yeah, simply by looking at this equation. So that is your findings. You tahu, this is what you need to have. High selectivity, in this case, instantaneous selectivity, okay, and high Kd, low Ku. And Ca concentration of A to the power of A must also be high. Ni pun mesti high. High, high, low. That is the situation that you should have. You want high Kd, low Ku, high Ca. Okay, then only knowing that condition, we're going to choose our best reactor, the most suitable reactor. We can choose, if it's liquid phase, we want to have high S, IS, the solvent as diluent is used. Therefore, the diluent should be kept as low as possible, maybe no need at all, yeah, to allow the Ca to be as high as possible. So you have the A here. And for that, since we want to have high Ca, we are not going to choose CSTR, all right? Because theoretically in the CSTR, the concentration is always at its lowest. Because CSTR, it works like this, flow in, flow out. The concentration of the Ca is always at the lowest. Dia masuk, react, keluar, masuk, react, keluar, masuk, react, keluar. That is the fundamental theory of the CSTR itself. But for the batch system, apa yang you masuk, you can choose to have as high as Ca as possible bila you masuk dalam. Of course lah, let it be. Dia react lah, biar at that specific residence time. Tinggal lah berapa lama. Of course, the Ca will be reducing. But you control the Ca as high as possible. Masuk mula-mula tu. So you may choose batch if it's liquid phase. If it's gas phase, so you may choose your PFR, gas phase. The Ca going to be as high as possible with high pressure. Okay, so the high pressure will give you high Ca. And of course, you want to have your Ca as high as possible. So you may choose to put in your pure Ca without any inerts. Kalau you ada inerts dalam tu, bermaksud relatively, your concentration of the A containing in total ada pula inerts lain, of course the percentage will be lower. Tapi you nak high selectivity, so your A tadi tu must be pure, tak ada inerts. Mungkinlah. Ini baru teori, bayangan what you need to do. Yeah, without inerts, no need possible to ensure as high as Ca as possible. Any questions before we proceed? Okay, nak tanyalah. Fazlika, any question? Yeah. High five.
No, doctor.
Tak ada, okay. Umaira, any question?
No, doctor.
No, doctor. Pandai korang, no, doctor tak kena kick out. Mirza, any question? Mirza, any
Doctor,
question?
tak ada.
No, doctor. Okay. Afsar. Dah sampai puncak dah gunung?
Setakat ni belum ke doktor, tengah hadam lagi.
Oh, tengah hadap. You. I ingat ke setakat ni belum lagi sebab saya faham semuanya. Rupanya tengah hadam pula. Daniel. Dia geleng je. Okey lah tu. S1. Geleng. Mikrofon tak okey. Akasha.
Yes, I have, doctor. Doctor, can you elaborate
Yes.
more on why we chose batch instead of CSTR? Because I couldn't imagine it very clear why in CSTR the concentration will be at its lowest.
Okay, in CSCR, I repeat, thank you so much for that question, Mr. Akasha. We have this CSTR, it's a STR here, but we have the word C there because we have continuous flow in FA naught, then continuous flow out, FA. Alright? Due to that continuous, maksudnya bila dia masuk, tak adalah pula dia kata, okay, stop, I tak nak keluar, I tak nak keluar, I nak duduk dalam. Tak ada. Dia masuk, dia keluar. Masuk, dia keluar. Alright? So it's theoretically, we assume that concentration of the A is always coming out. Tapi the reaction must be as fast as possible, ya, dalam reactor itself. But for the batch reactor system, since we want to say that the concentration of the A is high, so we may choose to say you masuk siap-siap kat sini high. Yeah? When you have initial concentration high in the beginning, then for batch system, the possibility of having the desired product produced is also high. Okay? All right. Nazrin, you have any question, Nazrin?
Tak ada, doktor.
Okay, Nada.
Tak ada, doktor.
Alright. Lepas ni saya nak tanya, semua ni saya nak tanya. Tak ada, kenapa tak ada? Najwa.
No, doktor.
Why? You geng Afsal ke? Belum hadam?
Doktor.
Amira?
No, doktor.
Amira? Got question?
No.
No. Why? Geng Afsal atau faham semua?
Tengah hadam juga.
Mashita? Thank you. Mashita?
Ya, doktor.
Any question?
Ya, doktor. Saya tak faham dekat liquid phase tu yang untuk diluent should be kept as low as possible tu. Macam proses ni tak faham itu.
Okay, to increase the selectivity, solvent as diluent is used. So the diluent should be kept as low as possible. Okay, because some of the component, it comes together with a solvent. Solvent too, it could be water. It could be other solvent like alcohol. So since we want that pure concentration of the component A, so kita nak as high as possible, so we want to reduce the diluent or the solvent. Yeah, certain chemical component it cannot come as itself sendiri. Mungkin dia kena dissolve dalam water ataupun dia hanya dissolve dalam alcohol. So the alcohol can be considered as solvent. Since theoretically we want to increase the selectivity, the concentration of the A itself must be as high as possible. So one way is to reduce the solvent concentration. Thank you, Miss Mashita. Do I answer your question?
Yes, doktor. Thank you.
Very good, very good. Camelia, do you have any question?
No, doktor.
Why?
Tengah fahamkan.
Tengah faham. Okay. So, lepas ni saya tanya seorang-seorang, you faham berapa peratus? No rain. You have any question?
Ada, doktor.
Yes.
Yang untuk gas phase tu, so dia punya suitable reactor is reactor yang mana?
Apa again your question for the gas phase?
Yang for the gas phase,
Mhm.
which reactor yang suitable? PFR or batch or
Alright.
etc.
Very good question. Yeah, normally the operation of the batch reactor system jaranglah kita buat batch gas sahaja. Yeah, it could be gas liquid, but normally if you are dealing with gas, choose PFR. Plug flow reactor. Very good question. Faiz. Thank you, Azra. Faiz. Faiz. Oh, mic rosak kot. Faiz ni mic rosak kot. Dia menyesal saya tanya Faiz. Nanti kena kick dia out. Tak apa, saya bagi chance dia. Dia betulkan mic. Azri. Azri, do you have any question?
So far no dok. Tengah
Okay, understanding level? Level understanding?
around
20,
80%. Something like that.
80%. 80%. 18. 18 ke 80?
70.
Oh, 70. Gak tu. Oh, very good. Hanani. Cicak pun kata betul. Bunyi cicak ke? Hanani, do you have any question?
Sebenarnya soalan saya sama dengan Akasha tadi, tapi sebab doktor dah jawab, so saya tak ada soalan dah lah.
Alright, very good. Shadiana.
For now tak ada lagi. Kena buat tutup
Okay, your understanding? Understanding you?
45%.
45. Okay. 5% lagi 50%. Very good. Syafiqah.
Tak ada lagi doktor.
Okay. Why?
Maybe sebab kena buat tutor dulu kot.
Oh, maybe sebab
ada
buat
soalan
tutorial
tu.
dulu ya. So I'm going to post that. Very good point you bagi sini. I'm going to post after this tutorial file siap-siap. Saya tak letak sebab tutorial file saya dah ada jawapan dalam tu. So saya nak kena bagi tutorial tanpa jawapan, nanti saya letak dalam files ya. I'm going to put that in class materials and in files ya. Okay, very good Syafiqah. Afifah. Okay, understanding level?
50%.
50%. Very good. Syafiq. Syafiq. Abu Hassan kot. Syafiq.
Saya ke doktor?
Yes. You Syafiq Abu Hassan ke?
Saya Syafiq Abu Hassan.
Okay. Alright.
Doktor, saya nak tanya, untuk gas phase kan, biasanya kita belajar kalau lagi higher temperature, maksudnya reaction tu jadi lagi tinggi, betul? Tapi
Lagi higher temperature. Yes, very good. Yes.
Tapi kalau dalam PV over RT ni, maksudnya lower temperature akan hasilkan lagi tinggi produk concentration.
Okay, kalau PV equals nRT. So here we have PV equals to nRT. Then we bring over the V there and bring over RT to the left. So we have P over RT equals to the NV. The NV is the concentration. So we have P over RT is equivalent to C. If the concentration is high, the temperature is high, the concentration is low. The A here is the reactant. When you are talking about the high temperature giving better reaction is referring to your product. Now we are referring to our reactant. Simply by referring to the ideal gas law, P over RT is equivalent to your C. Because we are referring to your reactant concentration, so you have to prepare your operating condition to be as suitable as possible because we want to have high concentration of C of the reactant A. So what do? The temperature is lower kat situ. Tapi pressure, since it is at the numerator, not denominator, to have high C, so high pressure. Ini maksud dia. Because when you are dealing with gas phase, you're also dealing with pressure. Why? Because the pressure or the partial pressure, remember partial pressure is the representation of the concentration of that component in gas phase. To answer your question, Mr. Shafiq? Oh, laju kot,
Boleh kot
laju,
faham.
laju.
Ah,
Boleh kot faham. Kalau nak faham lagi, lepas ni dengar recording, okay?
okay.
Okay, last round. Atrisha, any question?
So far no, Doktor.
Okay, understanding level?
50%.
50%. Very good, thank you. ASEAN?
Yes, Doktor.
Any question?
No. So far,
No? Understanding level?
maybe 50%.
Maybe, maybe tak sure. Ashikin, thank you ASEAN. Ashikin,
Yes, Doctor.
any question?
No.
Okay, understanding level?
50%.
50 Oh, Afifah tunjuk 70 tu. Fazlika. Last.
Yes, Doktor.
Any question?
So far no.
Understanding level?
55%.
Ditambah jiran sebelah 50, 55%. Okay, very good. Thank you. Even though it's 55, 50, still very good, yeah? Because I heard a lot of comments in class, tak faham. Banyak komen student cakap, kelas tak faham. So nak faham, kena buat exercise. Satu. Kemudian, bila dia buat soalan, baru dia faham. Yeah, when you reach 50%, so consider very good lah. So you put your focus there. Okay, last round. Mr. Faiz, mikrofon you rosak ke? Mr. Faiz. Oh, mikrofon rosak. Dia angguk je. Doktor, I need to go to the toilet. Okay. Bila dia pergi, Imran dia pergi, I pun tak perasan. Thank you for telling me. Faiz, mikrofon you rosak. Please do something, yeah, with your microphone, yeah. I got students final year, microphone rosak, nak meeting dengan I kata I tak nak meeting dengan you. Lepas tu dia pergi Shopee, dia belilah pula, no bukan video, kamera tak ada, dia beli kat Shopee kamera, microphone okay. So please do something, yeah. I'm gonna give you 1 week, next week, your microphone dah okay. Alright, thank you so much. Very good. See you again next week. Assalamualaikum warahmatullahi wabarakatuh. Bye.
Thank you, Doktor. Thank you, Doktor.
You're welcome. Thank you, ASEAN.
Thank you, Doktor.
You're welcome, ASEAN. Thank you. Apa tak sebut tadi?